Okay. Okay. So the next talk is minimizing the impact of dataset shifts on actionable explanation. It's joint work by Meyer, Suraj, Srinivas, Himabindu, Lakkaraju, and the speaker is Meyer. Welcome.
Hi everyone, I'm Anna. I'll be talking about our paper. So to get started, I'm going to ground us in a specific example. So let's say that there's a bank, they have some data maybe about who they gave loans to in the past and whether those loans were repaid. And they're going to train a model to use, and they're going to use this model to make decisions about who to give a loan to in the future. For the sake of this talk, let's say that this loan application was denied. A natural question then becomes, why was this application denied? And in fact, this question is one that in many jurisdictions, the bank would be required to answer. So in the US, we have the Equal Credit Opportunity Act, which requires an explanation in the face of an automated decision. And the European Union's GDPR behaves similarly. So we often get an explanation that's sort of a feature-based explanation. So in this example, we would have income and debt as factors that are counting against this person, but maybe their credit score is good and is counting in their favor. The problem that we're interested in for this paper is what happens if, say, 6 months or a year down the line, the bank gets updated data about the last 6 months or year of lending. And now they're going to use this updated data set to train a new model that they'll then use for all future loan decisions and the corresponding explanations. So what we're interested in investigating is whether these two explanations are similar. How stable is the explanation between the two iterations of the model? And in particular, the reason why we might care about this is because explanations are inherently, they should be actionable. So like if I get that original explanation because my loan was denied, it will sort of guide my process towards how I want to modify my profile so that maybe I'll be approved for that loan in the future. And so the thinking here is that if the explanation shift is drastic, if the two models are relying on really different features to make their decisions, whatever the original explanation said, that might be less likely to actually help me get the decision I want in the future if I'm making decisions based on that first explanation. And so of course, some explanation shift is likely inevitable, but we're curious how big that shift has to be. And so formally, how much do the explanations for a model f of theta 1 trained on a dataset D1 change when you retrain on a slightly shifted dataset D2 and end up with a new model f of theta 2? So as a preview of what we find, so the first factor we identify is we find that dataset shift size determines how large this explanation shift will be. We also find that the value of the weight decay parameter you use in training is influential. And then finally, the smoothness of the activation function plays a big role in how big the explanation shift will be. So for the rest of this talk, I'm going to show you how we theoretically derive that these three factors are important. And then I'll walk you through some of the experiments we did to show that these factors and others actually hold in practice. Before diving into that theoretical analysis, though, I should get a few preliminaries out of the way. So one might be, I've sort of given intuition of we're going to have some feature-based explanation. More formally, we're going to be looking at gradient-based explanation. So input gradients and smooth grad are two examples there. So sort of directly looking at the model gradients with respect to the input. And then we'll also be looking a bit at perturbation-based explanations such as Lyman Schaap. But there's previous work that shows that all of these different explanation methods can sort of be viewed as generalizations of model gradients. So for the next portion of the talk, I'm going to be exclusively talking about model gradients and sort of using that as a proxy for explanations more generally. So to reformulate our question, we're looking at how much do the gradients change between these two models. So to do this, we're going to take a three-step approach. We first need to quantify the size of the data set shift. From there, we'll be able to measure the expected parameter shift, where theta2 is the parameters of the new model, and theta1 are the parameters of the original model. And then from there, we'll be able to bound the quantity that we're really interested in, that is like the size of the expected gradient shift. So for this first step, we have a theorem. So I'll state the theorem and then sort of walk through what the different parts mean. So the theorem says that we can bound the parameter shift between the two models by the quantity on the right. So the square root of the Lipschitz constant of the first model times the distance between the two data sets divided by gamma plus c. So to walk through this, this is the Lipschitz constant of the original model defined in the usual way. For data set distance, we're going to use this definition here. So if you think of D1 as having a fixed order, we're going to consider all possible permutations of the points in D2 and find the ordering of the points in D2 such that if you match up the points 1 to 1 and take the average L2 distance over all possible points, we want to minimize that distance. Gamma is a weight decay parameter, so we're going to be looking at a regularized loss function. And then finally, C is just a small problem-dependent constant. To briefly touch on the other assumptions, the third assumption there, that the learning algorithm returns a unique minimum, that's one that I'm going to be talking about, that assumption and its feasibility later on in the talk, so stay tuned. But the idea with this theorem is that we can now bound how much the model parameters are going to shift. And that's helpful because we can use that for this next lemma. And this lemma says that the expected gradient shift for our two models is upper bounded by the gradient parameter Lipschitz constant, so L of theta d, times the parameter shift that we bounded in the last slide. So again, to walk through this, the first thing that we should define is the gradient parameter Lipschitz constant. And so this is one of our contributions defining what this constant is. And so what we're going to say is it's the expectation over all possible theta in some parameter set, and then the expectation over all x in our input distribution. And it's going to be the gradients of the model with respect to theta and x. This parameter set, we use just the line connecting the two models that we're dealing with. You could have a more expansive set of parameters, possible parameters, but we stick with this to make the analysis a little more straightforward. So this is great. We've found a way to bound the expected gradient shift for our two models. The caveat here is that how do we actually compute the gradient parameter Lipschitz constant? We're taking multiple expectations. That's not going to be straightforward to compute in most cases. In our paper, we do show how you can exactly compute this for neural networks with one hidden layer. I'm not going to go into the details of how we do that here, but the intuition is that this gradient parameter Lipschitz constant is very related to the curvature of the model. So for some intuition there, if you have ReLU, the gradient parameter Lipschitz constant is going to be infinity because it's not continuous. If you use a different activation function, so in the paper, we specifically look at soft plus. So ReLU is soft plus with a beta constant equal to infinity. So if you look at soft plus with a large value for beta, you're going to have a large gradient parameter Lipschitz constant. But if you are using soft plus with a small beta constant, the gradient parameter Lipschitz constant will be small. So the intuition here is that the activation function you use will help control how much the gradients shift. So to recap, we identified these three factors. And what we're going to do is, before diving into how we validated this empirically, there's a few more practical considerations. So the first one is model multiplicity. There's been previous work showing that if you train multiple neural networks and you use different random initializations for the two of them, even if everything else is the same, you might end up with very different models and very different explanations. So to get around that, we have a couple of techniques. One thing that we do is we use the same initialization for both the original and the shifted models. Another version is we do fine tuning. So we train our original model, and then rather than starting from a random initialization when training the second model, we start just with the first model weights and then continue training until the loss stabilizes. The second consideration goes back to the assumption from our first theorem. And if you recall, that assumption was that our optimization process is able to get to an exact unique minimum of F. So in practice, we use approximate minimizers like SGD, so that's not going to happen. We try to simulate this in some of our experiments, not all of them. We try to simulate this by training for many, many epochs and essentially overfitting the model. So trying to adhere to that theory as close as possible. And then we do the more realistic model training in a separate set of experiments. Okay, so before the results, I'm going to describe the 4 sets of experiments we do. So the first one is where we try to validate the theoretical findings. We try to stick to the theoretical assumptions as closely as possible. So here we're going to be fine-tuning to sort of minimize any multiplicity effects. We're also going to be training for a really long time to try to reach that exact minimum. The second set of experiments, we extend to realistic training setups. So only training for a realistic number of epochs and trying not to overfit like you would do in practice. We also extend to complex explanations. So rather than just looking at gradients, we actually look at feature-based explanations that you would actually present to an end user. And then in our final set of explanations, we're going to look at how other hyperparameters influence this. So sort of saying we were able to identify some factors theoretically, but what other factors can we identify experimentally? And then we look at 3 different data sets, all binary prediction tasks. The 2 that I'll be talking about in this talk are HELOC, which is a credit data set that predicts basically the risk of giving someone a loan. And then the WHO data set, which is data that predicts whether a country's life expectancy is above or below the median based on economic and social factors. We look at 2 types of data set shift. We look at Gaussian noise, which is really nice because that allows us to exactly control the size of the data set shift. And then we also use the WHO data set because we have data for multiple years. We construct a temporal data set and look at that paradigm. So our first set of experiments, the really strict theoretical assumptions. This first graph shows results for the HELOC data set. So the x-axis is the standard deviation of noise, so the size of the data set shift. And then the y-axis is the gradient similarity. So a higher score indicates that the gradients have shifted more, that explanation shift is larger. So the first thing we notice is that as the data set shift increases, gradient shift increases as well, as expected. And that's just the general upwards trend on all of the different lines. The second thing we note is that, so the different lines are different values of weight decay. If you use no weight decay, so gamma equals 0, the average gradient shift at this point is about 10 to the minus 1. If you use the largest value of weight decay we could find that didn't impact accuracy was gamma equals 0.01, and the gradient shift was 10 to the minus 6 there. So a really, really big difference just coming down to weight decay. The accuracy for the models are very similar for all of these cases. We see similar results for curvature. So here, we use different activation functions for the different lines on the graph. And so what we see is that when you're using ReLU, the gradient shift is much larger. With soft plus, it's a smaller gradient shift. So our next set of experiments are going to be the ones looking at more complex explanations rather than just gradients. So if we have a model, we might do something like this. And so this visual is showing the magnitude of the gradient for different features along with the corresponding direction. And we might say, we're going to present the top K, so in this case, the top 3 features to the user. we'll have a similar thing for our second model. And what we're going to ask is, we have one metric that's called sign agreement. And what that asks is, of the features that are in the top K, so the top 3 in this case for the first model, how many of those features have the same gradient sign in the second model? So they don't have to be in the top K for the second model, they just have to have the same sign. So here, features 3 and 5 have the same sign in the second model, feature 2 has a different sign. So the sign agreement score would be 2/3 here. So now we have, in these graphs, the x-axis is still the size of the data set shift. The y-axis is now the sign agreement score. So a score of 1 is perfect. And so the first thing we note is that as the data set shift increases, explanation stability decreases, as we expect. The second thing is that weight decay still matters. There's still a clear hierarchy of the different weight decay values. And then finally, smooth grad is noisier than saliency. So paradoxically, we think this is because smooth grad is sort of adding noise, and maybe that added noise cancels out the data set shift effects. We have data for the temporal shift here. So what we see is that smooth grad outperforms all of the other metrics on sign agreement and also other metrics that I didn't define here. So the explanation choice also really matters. So we've talked about all of these factors that we identified theoretically, but what about other training choices? So we have like learning rate, epochs, etc. I'm going to give just a small set of our results here. So what this graph shows, on the x-axis, it's the number of epochs we've trained for, and on the y-axis, it's that sign agreement score. So a high score is better. The first thing we note here is that the maximal explanation stability occurs at different epochs, depending on which learning rate you use, where the learning rates are the different lines on the graph. And so the takeaway here is not that we're going to prescribe, like, if you're using this learning rate, you have to train for this many epochs. It's a lot more complicated and data set dependent than that. But essentially just saying that the choice of hyperparameters is complex. And if you want to be sensitive to explanation stability across retraining your model, it pays to be careful about what combination of hyperparameters you're using. So to conclude, we've talked about the theory behind what factors impact explanation stability. We've showed that these hold in practice. We've showed that they hold in practice when we're looking at real explanations and not just gradients. And then finally, we've dug a little bit into how other training hyperparameters fit into the picture. Thank you.
Okay, next, I'm going to invite myself to discuss this paper. All right, the motivation of this work is very clear. Actionable explanations should be stable. Like if a person is told to do one thing, but later on he's asked to do another thing, the person has to be, be very confused, right? So this, Anna and his team has done a lot of work, both theoretically and empirically, to determine the factors that influence explanation stability. So I found it very interesting, for example, large weight decay, that helps, lower curvature activity function. Those are mean results related to theory, and also small learning rate, large batch size, early stopping, and so on. And also, turns out that actually the fine tuning is better.
Fine tuning is better.
Fine tuning is better. Okay, but in general, I feel those techniques basically to find a solution in a relative flat space, flat part of the solution space. That's my intuition. I do have some question. The first question is more kind of general. Explanation should be faithful to the model, right? Because it's supposed to help people understand model, but the model will change when your data change. But now you want explanation not to change according to the data change. So that's somewhat, contradiction in the conceptual level. That's the first question. Second question is that Now, if you really want to enforce explanation stability, can we just include it in the loss function of the retraining or fine tuning, right? This is what some researchers are doing in something called explanation guided learning. So that's my two questions. Thank you.
Thank you for the summary and those questions. So to address the first one, I have a couple initial thoughts. So the first one is that explanation faithfulness is something, and sort of like, are explanations doing good things at all? I think that's still a question that needs to be explored a lot in the literature. And so clearly, if your model is shifting, your explanations should also shift. I think the perspective we're taking here is that a lot of times there's multiple models that will do equally well on a task. And so if you're retraining your model, you might end up with a drastically different model and drastically different explanations, even if there's actually a different model that would do really well performance-wise on the new data set, but be much more similar to your original model and sort of having those similar explanations. So it's sort of like, yes, it needs to change a little bit, but how can we minimize the amount of change while still keeping accuracy in mind? For the second question, I think that's pretty interesting. I'm not familiar with that line of work. But yeah, it sounds like something I should look into.
Questions from the audience? Oh.
Yeah, thanks for this presentation. I had like sort of two related questions on the theory part. So one is like, is there any intuition for how or why is the regularization weight showing up in the bound that you had in the first theorem? And the other question was like, in defining your, capital L of theta comma d, you had an expectation over theta. So what's like the probability measure over the set of parameters over which you're computing that expectation?
So to address the second question, when we talk about the set of possible theta, we're thinking of that as a uniform distribution over all of the theta, just on the, if you were to draw like a linear path between the two sets of models. The first question was about what's the role of weight decay. I would have to look that up. I can talk to you offline about that if you're interested.
There. In the middle.
First of all, thanks for the nice talk. So I have two questions. In your theory result, it somehow appeared that you are assuming the data sets, the two different data sets are of the same size, at least in the definition of the distance. So my first question is, does it, like your result, does it extend to the case where the databases are of different sizes? In particular, one data set is like way larger than the other. And the second question is, perhaps I'm not completely sure I understand how do the gradients and the explanation are connected, right? Like, why don't you look at f theta 1x and f theta 2x only when they are different would the explanations come into picture, right? So those are my two questions. Thank you.
Yeah, so the first question about, I'm sorry, can you say the first one again?
The first question was regards to the database sizes, data set sizes.
Okay. So experimentally, we do look at data sets of different sizes. From a theoretical perspective, I would have to think about the theory a little more. I feel like hopefully it could be extended from a theoretical point of view as well. But in the experiments, we're not like explicitly defining the data set distance. And then the second question about, I'm sorry, what was the second question?
So the second question was how is the gradient related to the explanation?
Yeah, so lots of common explanation techniques sort of explicitly look at the model gradients with respect to that input. And then when you have that gradient, you basically say, So in this case, we're assuming that each feature is like just one value in the input. And so if you have certain features and the value in the gradient vector for those features is large, an absolute value, that indicates that changing that feature would change the model by quite a bit. So that's an influential feature. Does that answer your question?
Thank you.
All right, we have to stop here. So this concludes this first oral session. Thank you for your participation.